Okay, so today I thought we would look at the ellipse one more time. And there's some interesting geometrical properties of ellipses. Ellipses are wonderful. In this case, I want to look at 3 different ways to generate means, averages, using values of an ellipse, or using the various distance parameters that you might see on an ellipse. So let's suppose we have an ellipse, and let's say the given values for this ellipse are the periapsis, meaning the distance from this, say, pick a focus, to its nearest approach. So peri means close. And then the apoapsis is RA. That's the greatest distance from this chosen focus. And I want to calculate these 3 quantities in terms of these RA and RB. So RP. So notice that I know the apoapsis, I know the periapsis distances, and I want to find these other things from there. Okay, so one thing we might want to do is start by trying to write them down in terms of A, for example. We know the semi-major axis is very commonly used in elliptic problems, so why don't we start with that? And to do that, I'm going to recall our ellipse trajectory formula in the way I've drawn it, where the positive x-axis sort of is where phi equals 0. Then this is our general form. We've seen P before. It is the semilattice rectum, although we can kind of read that off honestly automatically, because when phi is equal to pi over 2, we know that we're up here, but cosine of pi over 2 is 0, so R should equal P at that point. So that's fine, but I want to write this in terms of the A's. So let's note that R evaluated at 0 is exactly RP. I mean, that is this distance when I'm at phi equals 0. But if I plug in 0 here, I'm going to get P over 1 plus epsilon, because that is cosine of 0 is 1. I also know that R of pi has to be RA. Well, that's going to be P over 1 minus epsilon, so that's not so bad either. Now recall that we did have a relationship we've derived earlier, which is that A, the semi-major axis, is P over 1 minus epsilon squared. So rewriting these in terms of these P's, we can find that RP, well, let's see, if I sort of swap out what P is here, I'll have a 1 minus epsilon squared over a 1 minus epsilon. That's going to be A times 1 plus epsilon. And then RA, by a similar argument, is going to be A times 1 minus epsilon. Oops, I had them exactly backwards. I was reading off of this when I should have been reading it more carefully, so swap those around. This was RA, and this one's RP. And that makes sense because we want RA to be the larger one and RP to be the smaller one, so that kind of checks out. Now, it's very easy to say, add these 2 together. Notice that the A times epsilon and the minus A times epsilon will cancel, and I'll end up with 2A. RA plus RP equals 2A. Of course, we already knew that because the semi-major axis, well, is half of this distance, so the sum of these should equal 2A. And notice that what that tells us is that A is half of this sum. In other words, the semi-major axis is the arithmetic mean of the periapsis and the apoapsis. So there's one average, one mean that comes out of this pretty nicely. Next, let's take a look at B. So we know from a previous relation that A times epsilon, where epsilon is the eccentricity, is A squared minus B squared. This is a property of ellipses that's known pretty commonly in like high school algebra, algebra 2, I guess. This thing, by the way, is sometimes called C. It's that distance, maybe I'll put it in orange. It's this distance here from the center of the ellipse to either of the foci. And so we can either write it as A times the eccentricity, or we can write it as this sort of strange Pythagorean looking thing involving A and B themselves. So what that tells me is that B, squaring both sides and moving stuff around, is going to be the square root of 1 minus epsilon squared times A. But look, I can factor this a little bit as the square root of 1 plus epsilon, and I'm going to go ahead and bring the a inside again. So I'll get one a there, and then I'll get another a here. But hey, these are exactly what we had just derived for RP and RA. This one's RA, and this is RP. These are the apoapsis and periapsis, respectively, written in terms of the semi-major axis, and the eccentricity. So this is actually just the square root of RA times RP. But that's another type of mean. This is the geometric mean. I'm taking the two values, RA and RP, I multiply them and take their square root. That's exactly how we define the geometric mean of two numbers. And it maybe isn't so surprising why that should be if we're kind of thinking of this almost like the elliptical version of a circle theorem that we commonly use, where we can sort of draw a altitude of a right triangle and end up with something involving the geometric mean. That's not what's happening here. I'm not saying this is a right triangle, but it is closely related to a right triangle that could be drawn there. So there's our geometric mean. And now let's try, well, there's one more mean that might show up kind of naturally. Let's try finding it with the semilatus rectum. Okay, so for the semilatus rectum, we now have that P is A times this factor. We've seen this before. And what I'm going to do is I'm going to multiply and divide by an A and factor the numerator. And you can kind of see where this is going, right? I end up with this 1 plus epsilon, 1 minus epsilon form that we've seen before. And this is exactly RA. This is exactly RP. And then I'm going to rewrite A using our relation here. This is 1/2 the sum. So now let's invert this and see what happens. I'm going to end up with this 1/2 coming to the top. And then I have a sum over a product. So if I expand that out, I end up with a very nice relationship that the semilatus rectum, well, 1 over the semilatus rectum, is actually the reciprocal average, or the 1/2 of the sum of reciprocals. But that is exactly the harmonic mean of these two values. So in this one ellipse, we have the arithmetic mean of the periapsis and apoapsis, we have the geometric mean of those, and we have the harmonic mean. And I just think that's real nice. It's nice that when some geometrical quantity or geometrical factors come in and give you a nice relationship with an analytical quantity. At any rate, there we have it. 3 different means that come from an ellipse without having to go too far beyond the basic geometry or distances involved. QED.